Well, today we're going to talk about chemical reactions, and we're going to get into some real chemistry, how chemical change takes place, and our first look at the rules by which chemical change is governed. A chemical reaction we can define as changing a substance or a bunch of substances into a new substance or some substances, and we're doing it by rearranging atoms. That's the only way it can happen. A reactant is a substance that exists before the reaction begins. There could be one, there could be more in any chemical change or chemical reaction. A product is a substance that's the result of the reaction, and again, there could be one product or there could be more. In chemical reactions, the number of atoms before and after the reaction has to be the same because of the law of conservation of matter. It can't weigh more after the reaction than it did before. And then the other thing is that the type of atoms before and after the reaction must be the same. And this sort of follows along with Dalton's idea of what an atom really is, or what an element is. Atoms can't change from oxygen to sulfur, for example, or from hydrogen to chlorine. A chemical equation is an expression that represents a chemical reaction. And its general format is this. We write on the left-hand side the reactant, or reactants, if there's more than one. And then we put an arrow that indicates the chemical change, and then after the arrow we write the formulas of the product or products. We call these paper and pencil models of chemical change chemical equations. And in math you've heard of equations too, so we might ask ourselves, how is a chemical equation like a mathematical equation? One way that it's like a mathematical equation is that there's equality. The number of atoms of each element is the same on both sides of the arrow. That doesn't change. So if I start out with 5 hydrogens, after I'm done I will also have to have 5 hydrogen atoms. The other question you could ask is, how is a chemical equation unlike a mathematical equation? The main difference is where an equal sign exists in a chemical equation, we have an arrow because we're really describing a change, and this arrow indicates that there's change taking place. It's not a static equality. It's a representation of the same atoms but differently formed. The arrow represents words that indicate action or change. Words like forms or becomes, produces, releases, liberates. We hear words like that that indicate there's some action taking place. There are some additional subscripts that we can put, symbols that we use as subscripts, to indicate physical state. For example, a little S as a subscript indicates solid. An L in parentheses as a subscript, liquid. Not a surprise that G means gas as a subscript. And then here's another one that might not make as much common sense, and that's AQ. That means aqueous. Something is an aqueous solution, which means dissolved in water. So here's an example of how we might write a representation using formulas for a reaction. This is written here in words. Hydrogen gas reacts with oxygen gas to form water vapor. So we'll write that out in symbols. Hydrogen is diatomic. Gas, subscript G, reacts with, so there's another reactant. So I'll put a plus sign to indicate that they're combining. Oxygen, O2, diatomic, and it's a gas. To form, there's an action word, so there's my arrow. And then water vapor. Well, water is H2O, and vapor is just another word for gas, so I'll put a little G there. Here's another one. Solid sulfur burns in air to form gaseous sulfur dioxide. Sulfur is not diatomic, so it's just S. Solid sulfur, looks like that. Burns in air, well, in air there's oxygen. Whenever something's burning, we're always going to think about O2, and it's a gas, of course. And it forms, so there's our action words, to form, gaseous sulfur dioxide. Well, sulfur dioxide is SO2, because that's the subscript 2 corresponds to the di, and then it's gaseous. It's a gas, so we put a G there. You guys try this one. Solid potassium chlorate decomposes when heated to produce potassium chloride and oxygen gas. Write it out in symbols. Here's your answer. Potassium chlorate is potassium's 1 plus. Chlorate is ClO3 with a 1 minus. So when we charge swap that, those just disappear and it's KClO3. It says it's a solid, so we'll put an S there. It decomposes. There's an action word, so there's my arrow right there. There must not be another reactant. To produce potassium chloride. Potassium's 1 plus, chlorine's 1 minus, so KCl, and oxygen gas. Oxygen's diatomic, so O2, and a little G for gas. Try this one. Careful of the wording here. Okay, here's your answer. Plants synthesize glucose and oxygen from carbon dioxide and water. So our action word shows up right at the beginning. We're actually listing the products first, but in the chemical equation, we write the products last. So our products are glucose, C6, H12O6, and oxygen, which of course is diatomic. They're being made from carbon dioxide and water, so those must be our reactants. Carbon dioxide is CO2, and water, H2O. Try this one. Here's your answer. Magnesium metal. Magnesium's not diatomic, and as a metal, it's a solid. Reacts with hydrochloric acid, which it tells us what that is, HCl. To liberate, there's our action word. Hydrogen gas, H2, hydrogen's diatomic, little G for gas, and form an aqueous solution of magnesium chloride. Well, magnesium's a 2 plus, chloride ion's a 1 minus, so our formula is MgCl2. An aqueous solution, well, it's dissolved in water, that means. Little AQ symbol goes for that. Hydrogen peroxide, H2O2, decomposes to water and oxygen gas. Try this one. Here's your answer. Hydrogen peroxide is H2O2. It decomposes. There's only one reactant there listed. Decomposes 2 as our action words. Water and oxygen gas. Water's H2O. Oxygen gas, O2. Little G for gas. One more. Solid carbon reacts with oxygen gas to produce carbon dioxide gas. Carbon's not diatomic, so just a C. S for solid. Reacts with oxygen gas, O2, little G for gas, to produce, there's my action word, carbon dioxide gas, CO2, little G for gas. These phase symbols like S and G and AQ, sometimes they're really important, sometimes they're not so important. When you have the information about the state, you should use it. If you don't worry about it. So let's say we were going to do this reaction. We were going to take hydrogen and we were going to react it with oxygen, and then we were going to make water. Well, here's a model that represents hydrogen, H2, and here's one that represents oxygen, O2. According to the law of conservation of matter and Dalton's atomic theory, we should be able to take apart these atoms, rearrange them, and then get water, the new molecule. Let's try it. Take apart my oxygen, take apart my hydrogen. I'll attach this hydrogen here. I'll attach this hydrogen here, and I have a water. But that's not all I have. I also have an oxygen, and oxygen isn't one of my products. So clearly this really isn't an equation. Let's look for a solution. Well, here's a possibility. What if I started out with 2 hydrogen molecules and 1 oxygen? Let's try and rearrange these. Well, now I can do it. With all the atoms that I started with, I get only water. So something had to be different. In my equation, actually, I needed to put a 2 here. There were 2 hydrogens, and in the end, I needed 2 here. 2 waters were formed. Here we're going to do this reaction, reacting methane, CH4, with oxygen. This is a burning reaction. This is what you do when the Bunsen burners are operating in the lab. The products of reactions like this are water and carbon dioxide. So let's take a methane, which looks like this, the black central carbon atom surrounded by this tetrahedral arrangement of hydrogen atoms, the little gray specks, and here's an oxygen, O2. Let's rearrange to try and make carbon dioxide and water. I know a carbon dioxide is going to have 2 oxygens attached to it, and a central carbon. Well, there's a CO2, but when I go to make my water, all I have is hydrogens. There's not enough oxygen to make this happen. Let's look for a solution. I know that I needed more oxygen to make the water that I was missing in the last try, so I'm going to add another oxygen molecule and see if this will work. There's my carbon dioxide, and now I have 2 oxygens left over. Well, with 4 hydrogens, that's just enough to make 2 water molecules. There are my products, carbon dioxide and water. So clearly, to balance this, to make it work like nature really would work, I need to start out with 2 oxygen molecules, and I'm going to end up with 2 water molecules. Those numbers, the 2's that I put there, well, those are called coefficients. And we can balance reactions without actually building models. You can manipulate these ideas of atoms in your head and balance the equations without having to actually build models. Well, this equation here is an example of what we call a balanced chemical equation. Once we find out how nature actually performs the reaction so that the atoms are all conserved and don't change type, we find that we have to add sometimes these little numbers that go out in front of these chemical species. Those numbers are called coefficients, and they balance the chemical equation. When we're balancing equations, we should never change anything but coefficients. Here's what I'm talking about. Let's say we were trying to balance this equation. H2O2 makes H2O plus O2. Now, if we want to bring this into balance, first of all, we'll notice that it's not balanced. I have 2 H's here and I have 2 H's over here. I have 2 O's on this side, but on this side I got 3 O's. I can never make this into balance by just like changing this to O and scratching out the subscript. O isn't O. O is O2 because it's diatomic. I can't change those. I also couldn't change it by scrubbing out that 2. That wouldn't work either because HO isn't water. Water is H2O. So you never change anything except coefficients when you're bringing equations into balance. Balancing equations isn't really very hard. It's pretty much common sense. The main goal is to make sure that the number and type of atoms on both sides of the arrow balance. Let's look at this equation as an example. On the left-hand side, I have potassium, I have chlorine, and I have oxygen. That means on the right-hand side, I better have potassium and chlorine and oxygen and nothing else. And that's the case. Now let's look at numbers. I have only 1 potassium on the left-hand side. On the right-hand side, same thing. I have 1 potassium. On the left-hand side, I have 1 chlorine. On the right-hand side, I have 1 chlorine. On the left-hand side, I have 3 oxygens, as indicated by the subscript on the KClO3. On the right-hand side, I have 2 oxygens. That's the subscript on diatomic O2. Now, to balance this, the only thing I can do, remember, is change coefficients. If I multiplied the O2 on the right-hand side by 3, that would change the number of O's to 6. The coefficient refers to everything that it precedes. So 3 O2's is 6 O's. If I put a 2 in front of the KClO3 on the left, that would also give me 6 O's. Now that's going to change something else because the 2 out here refers to 2 K's, 2 ClO3's as well. And so my potassium count now goes to 2, and so does my chlorine count. Well, I can fix that by putting a coefficient of 2 in front of KCl. That changes my potassium count to 2 and my chlorine count to 2, and that brings me into balance. That's the technique. Try this one. Phosphorus and chlorine, which is diatomic, makes PCl3. Here we see that same dilemma. We have 2 of one thing, 3 of the same thing on the other side. This is common in balancing, and so the trick for it is always the same. The least common multiple of 2 and 3 is 6, so I'll multiply the 3 side by 2 and the 2 side by 3, and that'll give me 6 Cl's on both sides. Putting the 2 in front of PCl3 also gives me 2 phosphorus, so on the left-hand side I have to balance that by putting a 2 there. Here's that photosynthesis reaction. This one's a little more challenging to balance. One thing I want to avoid here is trying to balance oxygen at first, because you'll notice that oxygen is in every single compound here. I think I'm going to work on carbon first. On the left-hand side I have only one carbon, but on the right-hand side I've got 6 carbons. All the carbon on the left-hand side is in CO2. All the carbon on the right-hand side is in the C6H12O6. So I can balance carbon pretty easily by putting a 6 there. Hydrogen's a similar situation. All the hydrogen is in the glucose, the C6H12O6. All the hydrogen on the left-hand side is in the water. So I can balance 12 H's by putting a 6 in front of the water. Now I'm going to worry about oxygen and see how I can make it balance. 6 CO2s gives me 12 O's, and 6 water gives me 6 O's, so that's a total of 18 oxygen on the left-hand side. On the right-hand side I have 6 O's here and only 2 here. Well, I need 12 more oxygens to balance 18, and a 6 in front of this O2 will do it. When you think about how balanced equations should be read and thought about, one thing is clear: the coefficients multiply the number of atoms in the formula they precede. So all the atoms in that formula. So the 2 in H2O, that means 4 H's and 2 O's. The 2 in front of H2 means 4 H's. Another example, if I'm looking at the copper nitrate here, it's 3CuNO3 2. That 3 means 3 coppers. It means 3 times 2 nitrogens. So that'd be 6 nitrogen. And 3 times 3 times 2, which is 3 times 6, or 18 oxygens in this formula. Another thing about balanced chemical equations is we should always reduce the coefficients to their lowest whole numbers. Most of the time they'll already be in their lowest whole numbers when we're done balancing it, but occasionally we can get carried away and end up with coefficients that could be reduced. Here's an example. 4H2 plus 2O2 gives 4H2O. It's balanced, but we could just put a 2 there and a 2 there and leave that as a 1. Well, here's a big word: stoichiometry. It's a word that's going to be part of your future, and just because it's big doesn't mean it has to be complicated or difficult. Stoichiometry really means mole ratios, which we've already seen before. In balanced chemical equations, just like in formulas, the coefficients in front of the chemical species give us a way to compare moles of one substance to moles of another. For example, in this equation that's shown here, I can make a number of mole ratios. Here's one. 2 moles of phosphorus reacts with 3 moles of Cl2. That's a consistent mole ratio. This reaction always works that way. You can depend on it. Here's another one. 2 moles of phosphorus will form 2 moles of PCl3. Here's another one. 3 moles of chlorine will form 2 moles of PCl3. So we get 3 mole ratios out of this equation.